Good afternoon, everybody. So after a couple of long days, is everybody doing okay? Hey, at least you've survived. My name is Raleigh Boreen. I'm a member of the Sports Car Club of America, been a member for many, many years, and I'm also on the SCCA's Foundation Board, which has an award that we give out every year at Formula SAE. We've been doing it since 1997, and the award goes to the Mentor of the Year, and it's called the Carroll Smith Mentor Cup. And this is an opportunity for students to put their advisor, their mentor, tell us why that person is just absolutely invaluable to you. The foundation, the SCCA Foundation, is the charitable side of our club. And it really is involved, first of all, we help with Formula SAE. We will be in October when you go to Lincoln, Nebraska for the workshop. We will be out there trying to help you and be one of the sponsors. We help with what we call Street Survival Teen Driving Schools. We have a Women on Track program. And we've got many other charitable causes that are automotive related that we really try to help. And that's with the Sports Car Club of America.
I'll find him.
Our involvement with the Formula SAE program includes the Carroll Smith Mentor Cup. And this award is one that the SCCA and the SCCA Foundation is excited to be part of. I had the opportunity to know Carroll Smith, and he was an interesting guy, let me tell you. We work with a group of professionals and professors and with the Formula SAE group in Pennsylvania to come up with candidates every year for the Carroll Smith Award. Now, how many people have heard about Carroll Smith before? How many people have heard of Carroll Smith? Well, Carroll Smith was a leader in automotive design. He was a leader in helping young automotive design and engineering students grow in their craft. And he was the consummate professional. If you look at anything in the 60s and 70s and even early 80s, automotive-wise, some of the greatest things that happened in the automotive world, Carroll Smith was involved with. Most important to students was the fact that he was the preeminent automotive American race car designer of his generation. But more important was the fact that he wanted to share his knowledge. He wrote several books over the years, and it ends up, you've probably read most of those, and he wanted to be involved with young designers and engineers. With Formula SAE, he was the ultimate mentor. When you came to the judges and talked to the judges the last few days, probably several of them had that strange-looking Australian hat. Well, that was his benchmark. That was his really identity, his logo, and he just wore it so very, very well. And he, like I said, from 1993 to 2003, he really led the design group for Formula SAE. And I hate to say it, but he passed away in 2003. He'll always be remembered for that Australian hat. The Carroll Smith Mentors Cup was established to honor special people who are mentors for Formula SAE students and teams. As I said, the award began in 1999, and the list of honorees is really the who's who of Formula SAE collegiate success. Would any of the former members or winners of that award, I'd like to have them stand up here. We've got several with us today, and I'll read off their names here, and then please, once everybody stand up, I'd like to give them a nice round of applause. We've got Alan Nye from RIT with us. He was the 2003 recipient. We have Peter Jones from Auburn University, 2006. Rob Sorum of the University of Kansas, the 2009 recipient. John Russell, the University of New Mexico, 2014 recipient. Please stand. And last year's recipient, Todd Nelson from Purdue University. When we talk about faculty advisors, when we talk about mentors, it really is them giving their time so that everybody can have just a great, great experience. I need to go to a page of my notes here. When we received the letters this year talking about the potential winner for 2025, the students talked about he fostered a culture of critical thinking. He has the ability to guide students towards their own discoveries. The students have gained a foundation that they will serve throughout their careers. He's a mentor who challenged us to very deep thinking. He embodies everything that his award stands for, the Carroll Smith Award. At this time, I'd like to invite up to the stage to receive the award, Professor John Vrabichanek. And the professor Peter, would you come up here and help me? Professor Vrabichanek is with Cal Poly San Luis Obispo. John, would you like to say something?
Thank you. So basically, I'm without words, which most of my team will tell you is a very odd situation. Just thank you very much. It was unexpected. And I know all of you, or a lot of you, have really great mentors. Cherish it. It's really important when you find one of those you really like. Hold on to them, learn from them, and remember what they gave you, and then give back the same thing when you get out there yourself. Thank you very much. It's great. It's really appreciated. And looking forward to hearing about the rest of the awards of everything that comes later.
Thank you very much. Okay, with that, I'm going to turn it over to the lead judge for the design, somebody that we met as a student back in 1997, Bill Riley. Come on down.
Thank you so much. All right, before we get started onto the top 3 design finalists, I'm going to invite Peter Gibbons up to talk about the Multimatic Vehicle Dynamics Award. Thank you.
That's okay. Thank you. How do you get the young engineers that work for Multimatic who came out of Formula SAE up here with me if they're here? If not, we can get going. So, first of all, sure. We value Formula SAE highly as a way of picking the top engineers. You guys should be very proud. There's no better training ground in our eyes than Formula SAE to generate a very high quality engineer, independent of whatever discipline you pick. These engineers are all out of Formula SAE. There's a couple more that haven't been able to make it up, but they've all sort of risen to pretty high levels within Multimatic in a very quick period of time, and their experience in Formula SAE has really helped that. We have mechatronics, fundamental damper design. So we highly value SAE, and I think you guys should really be proud of what you've achieved just getting here and competing and doing what you're doing. The Multimatic Vehicle Dynamics Award really sort of emanated from a desire to recognize after you have an overall vehicle design award, which will be coming up in the next few minutes. So the teams that use simulation to start from the beginning to set targets for powertrain, kinematics, aero, And then from that, you cascade down to a component level, and then from there, you do your simulations to optimize the whole process. And it's that iterative process that the teams that have risen to the top and are succeeding that they're using. So that's really the concept of the Vehicle Dynamics Award, is to sort of identify and reward the teams that are doing the best job of that. So this year, that team that is University of Wisconsin. So come on up. So these guys did a phenomenal job of using simulation from a target setting to cascading loads all the way then to optimizing the vehicle, torque vectoring, traction control. So hats off to these guys. This is the award. So with this comes this award comes a set of Multimatic DSSV dampers, that bespoke Formula SAE dampers, and also a day on the four-post rig. I think the day on the four-post rig is really one of the most powerful sort of tools that we can give to the team that wins this. It's a way of sort of opening their eyes to the modal characterization we use to understand a vehicle from a very simple first principles method. So congratulations, guys.
All right, thank you, Peter, and thank you, Multimatic, for sponsoring that award and acknowledging vehicle dynamics in the process. So next we'll transition to the design finalists, the top three. Like we discussed for the Mentor Cup Award, Carroll Smith, in the old days of design judging, back when I was doing this among many others, he did an excellent job, in my opinion, of looking at the car, distilling that knowledge down, and helping teach us all how to be better engineers. And to that extent, we want to kind of harken back to those days today and do that with you. But to give you more diversity of thought and more judges, we have some subject matter experts today here with me to talk you through. And the thing I remember most about that, besides being at Pontiac in the rain, listening to the design feedback, was I couldn't see anything that was happening. So we've attempted with technology to improve that situation. The screen's a bit dim, but we'll also be posting it online. So we'll be bringing the cars in reverse finishing order, and we'll be talking through what we liked, what we didn't like, as well as just overall design fundamentals about them. And we'll be having each of our several judges talk through things. You might find that the judges are not always in sync or have different opinions, and I think that that's really exciting thing about Formula SAE. It's not actually a formula. There's not actually a single solution that we're looking for. Carbon fiber monocoques, space frames, one motor, four motors. These things are all viable options. You need to tell us what you're doing and why, and we'll meet you there and talk through the de-engineering you did. From design, analysis, test, validation, all of the different steps of the process. And so if you do find conflicting ideas, just know that's fine, and there's different solutions to the problem, and we'll meet you where you are. So with that as a given, I'd like to now announce our third place design finalist and invite them into the tent. Carnegie Mellon, car number 299. Congratulations on third place. Actually, can you guys go back out and come back in a little bit farther back? I'll show you. See the screen? We've got the camera there. That's fine. Can you help them do it a little quicker? That's fine. All right, so we'll be working through our different design judges. First, I'd like to invite up Peter Jones. And They'll give you a quick intro of their background and what area they'll be speaking to.
Okay, so overall design is a new category for this year. It's been debated for a number of years as to whether we should look at the car as a independent assembly of systems or a dependent car with different pieces that work together in symphony as opposed to creating their own level of noise. Overall design includes conceptual design, choice of the overall sort of vague design concept that the car is trying to achieve, and it also includes the back end, how the car came out in terms of its fit, consistency, integration, and so forth. Okay, so on the design process, Carnegie Mellon did a good job of setting up skid time and mass goals to drive their design process. Their other goals seem to have been based mostly on achievability, so we're looking at a mix between the desired and the possible. Moved on from there to create a pretty nice surface of mass versus power versus downforce correlated with points. So they had some idea of how they were going to build a car to meet their goals. They had a pretty good mass model. A mass model would be if we select parameters or systems, what is the likely mass of the vehicle the result's going to be? Not exactly, obviously, but to some good level of approximation. Theirs did depend upon pre-selected modules, so as a kind of a semi-mass model, not with quite the degrees of freedom that we might hope, and that limited the range of alternatives that they might have selected. Okay, they had further down in the design process, they had a very good integration of vehicle dynamics and aero, so that we didn't have the vehicle dynamics people working independently of the aero people and then knitting it together and realizing that you couldn't make your skid time goal. They worked on the skid time goal with the two groups working in tandem. Okay, on the other end, let's look at the testing process. They had a good set of criteria for testing success. They tested both the power module all by itself as well as the whole car. So they're trying to test both systems and the whole car. And we're very careful to keep the driver in the loop as an essential component. That introduces a lot of fuzziness, but hey, it's there, so you got to do it. Okay, on the back end of the design, I'm going to introduce a concept to some of you, design for appearance. Doesn't sound very engineering-y, does it? But the fact is that engineers, just like normal human beings, are going to judge devices by proxy measures. Perhaps you might have been in a new car showroom and slammed the door to see if it sounded like the car was structurally sound. You didn't run an FEA on that car, but you do like the noise that slamming the door made. Okay, so those are called proxy measurements, proxy criteria. So for a formula car, designed for appearance is things like packaging, integration, form of the vehicle, the way the details are done. And the idea is that if they've done things like that properly, then perhaps the rest of the vehicle and its engineering design was also done properly as well. It doesn't hurt to advertise yourself. So these guys, nice form. In general, it's a pretty car. It's well put together. The panels, the nose, the tub, all fit together quite well. There are some loose hoses here and there, a bit of wiring wiggles here and there. It would be nice if those had been a little better cleaned up. There are some unfinished elements. I'll stand here so you can't see their heat exchangers, though you might come up and take a look later on. I guess you wanted to keep the car cool somehow. Okay, that's an expedient. Things like they went to some effort. They put epoxy in the edges of their flat pieces on the aero system, and we've got sanding of that epoxy to a smooth edge on these louvers here, but we've left it rough there. It would have been simple to run a power sander down the top there, but you've only got so much time in a year, huh? Okay, so in general, very impressive. These guys did a very good job. This is worth taking a good, strong look at.
All right, thank you, Peter. Next up is the esteemed David Gould.
Thank you very much. Well, good afternoon. My name's David Gould. As you might imagine, I come from England. We run a composites manufacturing company there, and also a lot of experience in making hill climb cars in UK, which in some ways are quite similar to these, or can be. Now look, sorry?
Can you pull up?
You can't hear me, sorry. Looking at this car, it's very attractive to look at. Lovely paint finish on it. The monocoque looks as if it perhaps could have done with a bit more finishing on it. And it's a carbon monocoque. And one of the things that is a very good judge of the quality of a carbon monocoque is the strength of the cockpit rim where it turns around the front of it, because that determines pretty well the stiffness of the whole structure. So if this is thin and not very much material there, it's probably not very strong. So worth a look at there. Other things about it that I noticed walking around the other night was the way it's got a system of push rods on it, which have what I would say were not a very nice way to not to do this, because we've got all sorts of points of failure in the middle of the push rod, which is a break here, bless you, and it's just a matter of when it breaks, not if it breaks, really. So I would be looking at something other than that. But besides that, the rest of the suspension components seem pretty good to me, and nice bracketry and nice lightweight, and very nice indeed. Moving further backwards, as you say, there needs a bit of finishing on some of the carbon bits, or where they've tried to fill the core with glue of some sort. And get to the back, we've got the same issue again with a rather unorthodox way of doing the push rods, really. Yeah. But other than that, the suspension, the quality of the manufacture looks good, and the design looks pretty good. We've got straight line load paths and all those sorts of things, and it's a good job, I think. One of the things that always makes me wince a little bit is bolts with thread sticking out longer than 2 turns of thread. And there's a couple of bolts here that are sticking about an inch past a thread showing, and you're just carrying that stuff around as a free ride. If you're accelerating it, decelerating it, cornering it, and everything, and it isn't helping you at all. So the best thing you do that is have the bolts the right length. Either buy the right length bolts or hacksaw them off and get them the right length. But other than that, I think it's a nice-looking little car, and well, what can I say? I think that will do me.
Thank you, David.
Thanks very much.
All right. Skidder, would you like to join us? That was great. That was perfect. Thank you.
All right. Hello, my name is Skidder Yeager. I started off in Formula and then Baja, and have spent my career in internal combustion and hybrid and even electric motorsport. And I would like to take this car as an opportunity to actually talk about tech inspection. So we have a full monocoque design here. So some teams that are monocoques, the monocoque stops at the main hoop, and then they have a rear space frame. In the case of Carnegie Mellon, the monocoque runs all the way back to the rear impact. So the entire structure, the entire regulated structure except for the roll hoops, is carbon fiber. And it seems to me, and maybe your teammates who reverse engineer all of your competitors' cars can confirm or deny this, but it seems to me that the full monocoques tend to have an easier time passing the rain test. And passing tech inspection, all of the different steps that you have to go through to get the stickers, get on track, that's worth 675 points in my mind. All the dynamic points, they come to you after you pass tech inspection. And if I was working on an electric car, I might not follow 40 years of FSAE tradition where you only put the bare minimum of body work where the rules force you to, and you hang the powertrain way out in the elements, ready to be sprayed by the rain test apparatus with all of the high and low voltage components. You can do it. I know all of you here have worked very hard on that, have waterproofed, have weatherproofed all of those systems, you know, at the accumulator level, at the motor inverter level, at all of your low voltage level. But I would use body work. You know, if I didn't have a full monocoque like this, where the body work is automatically provided around that entire high and low voltage system, I would be thinking very strongly about wrapping body work around from the front to the rear of the car, regardless of what sort of structure I had on the car. And one more comment on monocoques. You might notice when you're reverse engineering all of your competitors' cars, we see a lot of monocoques in design finals. And you certainly do not need a monocoque to go to design finals. And I think the correlation there is the immense amount of work that the teams have to do to pass tech inspection and then to manufacture these often very complex structures that are forming the basis for the entire car. But it's not about what the frame is. It's about, this team went to finals, and in part their chassis team helped them get there because they really knew their stuff. They had a whole bunch of graphs and diagrams and calculations that proved to us that they really knew their stuff. They had testing and validation on all the different parts of the car, and they communicated all of that excellently. But at no point did I say very much about the car itself, talking about why this car jumped into finals. But in that sense, the monocoque is a factor because it forces the team to really know their stuff. So what I'm saying is, don't read too much into the correlation there. And yeah, congratulations.
All right, I'd like to invite Peter Gibbons up now to do vehicle dynamics.
Hi there. So my background, I'm a technical director of vehicle dynamics at Multimatic. I run the Sim Center. We have a 9-degree of freedom simulator in Novi, Michigan that we use to develop racing cars and road cars. And then my past before that was IndyCar racing. I didn't know the real world until about 14 years ago when I joined Multimatic, before I was in the world of racing. Really to talk about the vehicle dynamics approach of Carnegie Mellon, I'm going to keep it pretty simple. They used, from a simulation standpoint, they were very pragmatic in their approach to their simulation tools. They used a relatively simple point mass model for their optimization of the powertrain and things like that. And then they used a very high fidelity multi-body physics model, IPG physics model, that allowed them to do more detailed vehicle dynamics, optimize their vehicle dynamics, and also use it as a DIO, use it for driver training. And I think that's something that is a theme that I think you'll start to see. But DIL is a great way of optimizing a vehicle if your model is a high fidelity, but even if it's a lower fidelity, using for driver training can really bring things along quite quickly. So I think that's going to be a common theme you're going to see amongst these top three. And that's really it on my side. I think if you look at sort of a lot of this is a bit subjective at times. We also objectively, these guys made top 10 in skid pads. So I kind of like to look at skid pad because it's a bit sort of independent of driver capabilities. So the fact that they've been able to put a car together that's quite competitive as well and can be top 10, actually 9th, I think, in skid pad, that speaks pretty highly to their capabilities. So thank you.
All right, next up is Chris Patton.
Hello, I'm Chris Patton. I'm a dynamics and simulation engineer. I've worked in motorsports, but nowadays I'm working in the aerospace and creating simulations of rockets and spaceships and the like. I'm going to be talking about data, specifically how the teams collected the data and then how they used it. Carnegie Mellon here had a really interesting architecture for their data logging system. They've made they've made it all themselves. That's like a Pi W, if you're familiar with Raspberry Pis, and then you put a hat on top of that to get your analog to digital converters, and then plug in your various sensors like ride height, tire temperatures, and then that all communicates over CAN to their central logger. It's a really cool solution. It's going to be much lower cost than going out and buying something. That said, each team should make their own decisions. Like sometimes buying a Motec or using a vector system is the right decision. But they had a great system. They developed it themselves, and it's working well for them. One of the things that they a bit of struggle with is accessing the data. A lot of the people on the team who are in charge of logging the data are more the computer science types. And for them, it's easy to just write a Python script, load the data, and create all the plots you want. But that becomes a challenge for some of the mechanical engineers, and so then the data accessibility is not as good. So that's something that they're aware of, and they're working to improve. But it's one of the trade-offs you should think about when you're picking your data system. It's not only just how do you collect the data, but then how are you able to view it? Can you look at it quickly? Are you going to be making decisions over the course of a week or a day or 15 minutes? And the quality of your data access is going to determine that. Once they have their data, they're doing good things with it. They're using TTC data, but they know that the data straight out of TTC is not scaled properly. So they'll do skid pad tests and acceleration tests to get proper scaling for the coefficient of friction, the mu value. And they're doing a good basic job of that. For example, they're only doing a single skid pad instead of maybe doing multiple skid pads or doing that kind of correlation on autocross. Along with that, they have some interesting simulations and they have track data, but they're not putting them over the top of each other and looking at them. We definitely like to see that. It's a good next step, but we very much like what they're doing. Yeah, very well done.
All right, up next to talk about aerodynamics is Zach Aiken.
Yeah, hey, so I'm Zach Aiken. Worked in racing for about, 10 a dozen years. IndyCar, NASCAR, a bunch of weird stuff at Le Mans. And then currently have a little composites company in Southern California making parts. So done a lot of aero development over the years. As you can see, this car's full aero package, big rear wing, 4 elements, about as big as you're going to get away with, especially with the new rain light rules that everybody seemed to be struggling with, and big front wing. One of the interesting things when you guys can come and take a closer look at the car that we liked that they had done was raising the nose of the cockpit and giving a good gap to the center section of the main plane in order to feed more airflow into the floor. We see a lot of front wings that end up choking off the floor and a lot of CFD runs that show a floor which really isn't doing much. And so the fact that these guys had a bit of thought put into that, the way they're going to feed airflow through the whole car and that the entire system kind of works together was interesting to see. Good to see. One of the other things we talked to them about was they had set performance loss targets for the car in yaw roll steer, those kind of situations, which if you guys have had the opportunity to actually log data and look at what the yaw angles are of the cars as they're out on track, the yaw angles of these types of cars, because of the short wheelbase, are very high, and so it's very easy to have half the downforce switch off, as the cars are going through the corner, which is in many ways the most important part. So they had set a target for how much loss they wanted at different degrees of yaw angle and set that as a priority. So that's it's evidence of a more refined level of optimization in the car, and so a good indication that they've done their homework and they know what they're doing. Some of the other things we liked was taking the load cases for the individual elements, both like cone strikes as well as nominal load cases. I think most teams do that, but again, like the way they could articulate it to the judges in that was kind of above what we typically see. And yeah, again, we talked about some of the system integration trades between the tub and the aerodynamics, which we thought were quite good. You know, some of the things that we think could be a lot better on the car around aero was, you know, it's a four-wheel hub motor, so super dope, lots of power, great traction, but like we got coolant lines and power lines and brake lines and data lines all going outboard to all the wheels, and not modeled in CFD, and especially the way that they ended up integrated into the car. It's, I mean, the diffuser is the most tragic one, where there's literally holes drilled through the diffuser to run coolant lines across right where all the high energy air should be doing the hardest work. So, you know, the difference between what we have and what we think we have in CFD is likely to have a pretty high gap. And, you know, we want to see the teams working together. We want to see that the powertrain team, the cooling team, know that when they put their stuff there, it affects the aero. So we need to see the teams, the sub-teams within the car working together, talking about what the right trade-off is. You know, to run the coolant lines a few inches further forward and above the floor, you know, definitely would have been possible to run a lot of the electrical wires along the wishbones instead of kind of coiled up in a curly Q. Would have been, you know, literally just a few more minutes in the way that we tied stuff up. That would have been good to see. You know, from an aero side, we want to see validation. We were lacking a bit on that side in the full-size car that we have the performance we think we are, or think that we have. And then one of the other sort of more nits on the car, some of the wing elements are male molded, so the external surface finish is quite rough. And you can male mold stuff. It's cheaper, it's faster. That's cool. But you know, put a couple extra hours in, sand it down, make it smooth. You know, you can try to make an argument that the golf ball texture is somehow better, but we're going to push you pretty hard if you try and sell that to us. And since the CFD was unlikely to have that texture in it, the car shouldn't. So those kind of fit and finish details end up in aerodynamics making a huge, like those details is what David spends most of his life making sure every millimeter of every carbon bit just looks absolutely perfect, because the Formula One customers demand nothing else. And I think, you know, here we could have seen just a few more hours put into that. Some of the other judges commented on some of the end plates and stuff, but yeah, otherwise it's an attractive car, looks good, and it was pretty quick.
Thank you, Zach. All right, and last but not least, Adam Kwiatkowski to talk about powertrain.
Good afternoon, everyone. My name is Adam Kwiatkowski, and last but not least, so I had one question for everybody before I get started. It's hot, so an icebreaker. How many propulsion engineers calculated the energy points of putting an AC compressor on the car today? Anybody? Yeah, it was pretty warm. Texas teams are like, I don't get it. Okay. So I competed in this event from 95 to 97, which means this is my 30th Formula SAE, and really proud to be talking about propulsion. I also work in GM's propulsion engineering department. As propulsion engineers, we consider ourselves the keepers of the acceleration run, just like vehicle dynamics consider themselves keepers of skid pads. So I'll be talking about acceleration run a little bit. And you know, we also consider ourselves the spinners of the tires. So we have raging debates in the design group whether or not we should have 4 motors, whether or not we should have the capability to spin all the tires at whim. My personal opinion is that if you are a propulsion engineer in this competition, you should design a system that either puts the tires into slip or puts the 80 kilowatt box in the red zone all the time. So we'll be talking about that as well. The Carnegie Mellon's car, we split it up into 3 different areas. First, the overall propulsion system, and then motors and inverters, and then finally battery. So for the overall propulsion system, Carnegie Mellon did really well, 4.06 acceleration time. They said it was a little lower due to control issues. That's something I did want to talk about. You know, if you really want to slip all the tires all the time, you have to have more than one motor. And if you pick 4, you wind up with a pretty significant controls challenge. So hopefully your propulsion engineering team is both hardware and software strong. You know, keep that in mind if you pick 4 motors and you really want to go for the fastest time. The team integrated paddle regen, which is pretty cool. So there's like a lever on the steering wheel that allows the driver to select the amount of regen. There's also a launch control button. So there's a lot going on between your feet and your hands. And they actually put together a driver simulation box. so the drivers could get used to all the different controls, even while it was cold outside. So very, very cool. We like that. They wrote their own in-house torque vectoring controls, also something that we like. And they also said something interesting. They said, hey, when I asked, can you slip the tires all the time? They said, we were really motor limited last year, but the car was heavier. So that's, a really important point. You should match, the motor power and torque and the resulting gear ratio with how heavy the car is. And then they did have limited torque power plots by vehicle speed. So a note to all the teams, we really want to see that you understand what's happening at the bottom of the tire as you design the propulsion system. So do those calculations. You'll learn a lot about the car, and it'll really help you for overall system target setting. For the motors, they selected the AMK four-wheel motors FSAE kit, which is a solid choice. And they also set the gear ratio properly. They were very, very close to 20,000 RPM at the end of the acceleration run. So that's also something that we encourage everyone to do. Make sure you're managing the motor speeds and getting the most out of them, balancing tractive effort and then speed limiting. For the battery, they selected pouch cells because they had low DCIR, so low resistance. We love that. Basically, cells come in kind of like the energy form, which is what in the industry we'll put in a battery electric vehicle, or the hybrid form, which we'll put in a hybrid vehicle, and they have different resistances. So race cars want really low resistance, high energy over the road cars that want 500 miles of range, want the energy cells, and they're different. And if you think about the power to energy ratio in the cell, we want you to talk about that when you come to the competition. Their accumulator was non-structural. We see a trend moving towards structural accumulators. I like that. We actually did it at GM. If you look at the transition from the Bolt to the current gen Lyrics and Hummers, our battery packs are also structural. So they contribute to the torsional rigidity of the vehicle when you bolt them in, just because sometimes that part of the car is the most efficient place to stick a bar. So if you're trying to connect two things and the battery pack's in between them, make it structural, you'll save mass overall. They selected passive cooling, which I'm always a little bit leery about, but they had data to back it up. So they said they saw 50 degrees Celsius maximum at the cell tabs, and tabs are the right place to measure it on a pouch, not in the middle of the cell, so that was exactly the right answer. Cells get super unhappy over 60, so targeting 55, is very, very reasonable. And they selected the battery pack size of 6.7 kilowatt hours via LapSim. And a lot of teams are kind of trading off the overall energy of the pack with how much they need in endurance. And you do have a choice of how hard to drive in endurance. So coming prepared to talk about how hard you drive versus how big the pack is versus power to weight ratio. We love seeing those calculations in design. Great job, Carnegie Mellon. It was fun to talk to you all.
Thank you, Adam. Thank you, Carnegie Mellon.
I would go back out. I would go out backwards. Okay, we have till 7.
All right. Next, I'm proud to announce our second place design finalist is car number 204, Georgia Tech. Please join me in the tent.
I think if you go straight and then come back and make the turn, you'll have... You nailed it, guys. Thank you. All right, you can stay in or out depending on what you want.
All right. talk about Georgia Tech, I'm going to invite Peter Jones up to talk about overall.
I'm reminded that I failed to introduce myself with the Carnegie Mellon segment. I was Auburn University's advisor for both Baja and Formula for 26 years. Retired from that 4 years ago. I had decided I was going to leave collegiate design series behind. That attitude lasted for about a week. Called up the design captain and said, please let me come on back and continue to be part of Formula. So I guess what I'm saying to you guys is be a Formula lifer. It needs you. Okay, so Georgia Tech, let's talk about conceptual design for these guys. They had started off with event point goals, like many of you do. They did whole car parameter studies, looking for how close they came to those event goals. Did make a little bit of a minor slip. Well, actually, they made a slip in treating those parameters as if they are independent. Okay, so here's an example. Let's do a mass versus point scatter, and a number of you guys have tried that, and you know what a mess that turns out to be. And the reason it turns out to be such a mess is that, well, F equals MA, M is one of them, F is another. It turns out that F is really strongly correlated with M. So if you're going to claim that M is an independent parameter, then of course you're going to get a messy result. So did a parameter study using independent parameters. From this, they created system goals that, as a necessary result, were kind of open-ended and kind of qualitative. So this kind of gets us down to, we've all seen it, the formula model of every system designer, do as well as you can. And that works great if the systems don't really have to sweat to integrate. But as the cars get more and more complicated, then that's just not really the case anymore. Okay, on the testing side, these folks did a really nice job of failure modes and effects analysis. That's going to save you from a few endurance race failures. Did you guys finish? And they finished the endurance race. More in testing, they had a very objective test plan. Objectives that they wanted to meet and accomplish. As far as the design for appearance, you know, these guys show up and we've got all sorts of awful things to say about the design finalists, and so you're asking the question, how did they get to be the design finalists? And I guess the answer is, this is such a hard problem that you can always find something to quibble about. Perfection is still out there waiting for all of us. In this case, we have a car second place in design with no paint on the frame. You guys did a really nice job of standing it up so it looks kind of shiny, but you know, nothing shouts unready to race more than an unpainted frame. Okay, and then we've got a few other little things, some goop on the wire closeouts. The panel fit could have been a good bit better. We've got some tab welding, just sort of a touch messy. And you took off most of the aluminum tape, so that's good. But the car should be engineered to not need aluminum tape. You know, you do aluminum tape at race if you have to, absolutely. But gee, wouldn't it be neat if you'd caught that problem in design and manufacture and solved it before it got to be a field fix? Okay, and gosh, that's all the complaints I've got. You must have done a really good job. Congratulations, folks.
Right, well, this is a very nice looking car. It's a space frame. It's got nice suspension. Generally speaking, everything seems to be in the right places. I could quibble about a few little things, but the one thing that sticks out as not very nice at all, really, is this use of bits of wire to hold bits of car up, and it's really a pretty poor solution. And the day you see an F1 car driving about with bits of wire on it, that'll be the day. And it's possible to do all that, you know, make these things stiff without needing that. For example, the front wing, like, I hate to be critical about these things, but the front wing spar should be strong enough to easily hold itself up without any of these bits of wire. We shouldn't be, because the wire's spoiling the airflow of the rest of the car anyway. It's right at the front, and it's everywhere it shouldn't be. So, as I say, I hate to sound critical or negative, and I don't want to be negative because it's a nice car, but it'd be a lot nicer if it didn't have these bits of wire all over the place holding things up. That's all I'm going to say about that. Moving off, we've got even more wire holding the wing together or holding it in place, and again, that you shouldn't really need to have those sort of things. The structure should hold it up, and there should be spars and things inside it capable of doing this job. But it's a nice looking car, and it's got lots of nice features and lots of nice bits in it, and you know, I'd be quite pleased with it if it was mine, but I would get rid of those bits of wire. Okay, thank you.
Thank you, David.
Thank you.
All right, Scooter.
So was the car, it finished endurance, was it fast in endurance? All right. How about efficiency? How do you think you're going to score in efficiency? All right, we'll see. We'll see. So let's talk about the energy budget for this car. And in the electric competition, you have the incredible challenge if you have a tiny, tiny amount of energy compared to the internal combustion competition in order to complete the endurance event. And Georgia Tech has taken the approach of with a four-motor car, they have really maximized the amount of energy that they're recuperating through regenerative braking. And that has allowed them to use a lot more energy in order to go a lot faster around the track. And so where are you going to go from here when you've regained all of the energy that you can through braking, and you've got the pack sized in the car to go fast in endurance, and you want to go even faster, or you want to score even higher in the efficiency event? How are you going to figure out where the opportunities are? Well, they have done the analysis where they look at the energy that is being used to complete the endurance event, and they know the exact percentage that's going into aerodynamic drag, and they know the percentage that's going into rolling resistance, and they know the percentage that's being lost from the battery losses, through the inverter losses, through the motor losses, through the driveline losses, and basically from cell to tire. They know all the powertrain losses. They know how much is being lost in acceleration, and they know how much is being lost when you are going around the corner and all of the four tires are slipping, and that is consuming power and energy as well. And they have that breakdown, and that will be a tool that will allow them on their next car that they bring to competition to look for those opportunities. Where can we save energy that is disappearing through all of these losses? Where can we make the car more efficient in aero? Where can we make the car more efficient rolling, lighter for acceleration? Where can we make it more efficient every step of the powertrain, and then have more energy in order to go fast, in order to use less energy and score higher in the efficiency event? So we'll see how the scores come out later, and congratulations.
All right, next I'd like to welcome up Peter Gibbons.
Thank you. All right. So to me, from a vehicle dynamics standpoint, the most impressive thing about Georgia Tech was their approach to a really, really difficult problem, controls problem, traction control and torque vectoring. I think anybody that's looked at it in depth has realized it. On paper, it's pretty simple, but executing it is far from simple. So Georgia Tech's approach was really first principles. They've got a model-based control that basically dictates the amount of yaw moment they want to add. It's actually informing itself on the mu of the looking at you guys. One of the clever things is you're aware of the mu available, and that's sort of affecting your yaw moment request, your yaw request. And they're also using telemetry to sort of basically augment their optimization of their approach. I think that's incredibly clever. So these guys have taken a pretty difficult problem and done a really great job. And again, if you look at the proof in the capability, they were 5th in skid pad, which is pretty darn good. So that's really all I have to say. I just can't say how impressive it is, their approach to the torque vectoring. It's very, very, very high level.
Yeah, I second everything Peter said on the vehicle dynamic side, the controls. It's extremely impressive. I have to say, I'm a little bit jealous. You guys get to play with these 4-wheel hub motors and do all the cool controls. It's really cool what you're doing. On the data side, they really committed to having their data system make their data as accessible as possible and provide the most utility. So, as opposed to running Python scripts, they've made their own data viewer that gives them access to their data very quickly, and they're using it very quickly. Yesterday, when they're running acceleration and doing skid pad and autocross, they're run to run. They're understanding what the mu is of the track, and then they're updating their control system to take advantage of that. And in proper motorsports, there's never the proper mu, it's never the same. You always have to figure it out on the day. And that's something that they're doing a great job of actually using their data very quickly to compensate for grip changes of the track run to run. We'd like to see a little bit more correlation of other parameters on the car, use the data a bit more for the vehicle modeling side of things. That said, what they they're using a lot of driver feedback and data, and I think they know that the driver part of the equation is extremely important, and so there's a trade-off to be had there, and so it's a fair trade-off to make. Yeah, lots of impressive work. Very nice. Keep going.
Up next is Zach Aiken to talk aerodynamics.
Right. So another full aero package car. Not as aggressive on the side wings as we've seen in some others, and I think in some of the conversations with them, it was apparent that they knew they were trading off front wing downforce for floor downforce, which is completely normal, and a lot of teams don't understand that. It's really easy for the front wing guys to look good and completely just destroy the ability to make downforce in the center in the floor, and so you end up with a forward center of pressure that's hard to rebalance without putting just a ton of drag into the rear wing, where you've got the driver's head obscuring it, and it's got just a much harder life. One of the other interesting things that we thought was really good on this car, we saw they had pressure tapping data to correlate some of their models and analysis from early on to the full-size car, and so that, as I mentioned, I think on the last car, we want to see that full cycle from analysis, design, test, and validate. And that was one of the things that, there's a lot of ways to validate it. Pressure tapping is a really good indicator that your surfaces are making the pressures that they're supposed to, because you're measuring it directly. I'll just put in my pitch here that not enough teams flow viz their stuff. I think every team I talk to, I push to do that, and not enough teams do. And we'd love to see that more in competition, so that you can correlate the LIC contours from the CFD onto the surfaces. Are your wings really attached or not? Because transitioning to some of the things that weren't as good on this car, again, this, like Carnegie Mellon, the wiring and cooling routing is much more on the tragic side, where there's a lot of holes cut into the floor just to get the wires across. And it wouldn't have taken much more to run them in a much less intrusive way. And that's where we want to see that cross-system optimization, where everybody's talking to each other and the right decisions for the overall car get made. One of the other things that was unfortunate, it's pretty easy to see, looking at the leading edge of the floor, that the top surface is going to separate. It's not uncommon for a lot of Formula teams that the top surface of the floor looks like an offset of the bottom surface of the floor. and they're, the concern is on the bottom and nobody pays attention to the top, and a very sharp leading edge is the result. And so the way the radiators are positioned on this car, being just after that leading edge on the floor, the likelihood that you're getting losing a lot of dynamic head that's available into the rads wouldn't have taken much more to put a soft leading edge on the floor, even if it's not molded, even if it's just a piece of core that you lay up around a bit of a half round to give it a softer ability to attach. And then the only other things to give you guys a hard time on, again, super common formula thing, but it's always makes me sad. It's almost as bad as the wires, but is the gaffer tape on all the leading edges of everything is like the saddest way to meet the, was it 5 millimeter radius rule, whatever it is. We've got gaffer's tape hanging all along the front wing. We've got vortex generator channels in the foot plates of the front wing, and there's tape hanging a half-inch down into the airstream that's, I'm sure it's not modeled in the CFD. I would guess it's quite important. And here we are. This fully molded part didn't have to be there, but it is. And as I say, I'm looking out of the crowd because a lot of you guys are guilty. Just mold it in, put a little piece of core. It doesn't take much to make it a lot better. And again, we can see this one on the leading edge of the main planes and the end plates on the rear wing. So otherwise, car's super pretty. Like David, I think it's awesome. I'd love to have one.
Okay, I rated this car the best propulsion system here. So really, really well done in the propulsion powertrain category. Georgia Tech, the last time we spoke, they were number one in acceleration. Hopefully that sticks. 3.746 was the time. The car is blisteringly fast, and I asked, why didn't you go faster? And they said it was really cold yesterday. It's a great answer. Data to back up that the traction limit changed, not only with ambient conditions from where they tested, but also from our test track to the acceleration track. So outstanding understanding of the propulsion system and how it relates to the tires. They picked the four-wheel AMK motor kit as well, and the answer was because of simplicity. That's a great answer. We do make-buy decisions at work all the time. We want to have the capability to design absolutely everything in-house, but sometimes buying it is the right answer due to cost constraints. But if you have the know-how, it makes you a better buyer. So that's a completely acceptable answer. Outstanding wheel slip strategy. So I think the dynamicists talked about this as well. But even in a straight line, they know exactly how much torque to put to each wheel. Their control system is outstanding, and the interface, so the HMI to that system, is very, very capable, and they showed us what that looks like, and they're able to change tunes very, very quickly. The system propulsion voltage is also 530 volts, which we like. It's nice to have a nice high propulsion voltage. You can downsize cables, and I encourage everyone, think about that. What's the max voltage your motors will handle? And take that into consideration as you consider how many batteries you want to put in series and how many you want to put in parallel. Lots of times you can jack up the voltage just by wiring choices. They selected a 6.3 kilowatt hour battery, and they're actively derating. So during some events, they use all of it. During other events, they're limiting the amount of motor power because the battery is small. And I encourage everyone, again, to think about that. What size battery you want is a power-to-weight calculation, and again, we'd love to see those calculations. And they're the only team here to have a full energy budget. So one of the powertrain judges yesterday asked everyone, okay, you have so much energy in your battery pack, where does it all go on each one of the events? How much go to the wheels? How much go to this system, that system, through the motors, through the inverter, through other ancillaries, and they know exactly how much all of the energy flow went, which is great. And again, at the end of their fastest acceleration run, I won't give away your fastest one when you're testing, but their motors hit almost 19,000 RPM. So again, they're setting up the system to use all of the available motor speed, which is the right answer. Because they've had a similar system for multiple years, they really, really know it well. And I asked, you're running the same motor size front and rear, would you do something different? And yeah, it may be worthwhile putting a little more motor in the back was the answer, which is exactly what we do at work. we basically have a little more motor power in the back than we do in the front for wheel-wheel drive bias cars. I'll tell a funny story too. So in today's final review with them, which was after the endurance run, I asked, how are your thermal systems working today? It's a hot day, and you just finished endurance. And they said, they start to derate their motors at like 100C, but they were 90C at the driver change. Awesome. That means, they'll probably get close to 100 at the end of Enduro, which means everything's sized right and not overdone. Inverter, similar story, 50C derate, and they knew that, they were at 45C at the driver change. And I shared this with some of the other judges at lunch, and we all chuckled. 30 years ago at driver change, we'd be like, is anything smoking? Nope, send them back out. Okay, good. So lots of technological advancement and a lot of fun to see that level of understanding. For the battery, the only thing I could fault them on is that the battery is not a stressed member. Again, we'd like to see the enclosure pack, being part of the structural, chassis or frame. They selected pouch cells and are capable of 15C discharge rate, which is awesome, 15C. If you don't know what C means of discharge rates, look it up. It's sort of the vernacular in the industry now. It's difficult for us to talk to you if you only say like amperage. So really look up C rates. It's normalized to the battery size, and it's a nice way to think about things. If your batteries are limited to 3 or 4 C rate, they're not a power cell and they're not appropriate for racing. So think about that as you pick your cells. They put foam on one side of the pouch because you have to support a minimum face pressure and maximum face pressure. Pouches are a little finicky that way. And then a heat fin on the other, which is a really nice way to set up the accumulator. Spring on one side, heat sink on the other. And it was very effective. They removed the fan from last year to this year, and they're still only seeing 52C max temp on their tabs. Again, right in the range of what we like to see. And they didn't have to pay for a fan or water jackets. They also designed their own custom in-house BMS, battery management system, which is great. We love that. And they've increased the response rate with an Ethernet connection this year and had a lot more data on tap at a higher frequency. And they've also done real-time bus bar temperature testing. So once you get to this level of propulsion system design, making sure all the cables are the right size and none of them are a pinch point. You can think about the cables in the propulsion system like water pipes in a hydraulic circuit. They should be really big at the first node, and they get finer and finer as they touch each one of the battery cells, and they clearly had an understanding of that as well. So outstanding job. It was a thrill to talk to you all.
All right, now please join me in congratulating our first place design finalist, car number 203, University of Wisconsin at Madison. All right, Peter, do you want to join us in talking through overall systems?
Okay, I have got to tell you that this team building this car did the best job of open-ended, optimized conceptual design that I've seen in Formula SAE. It's a fairly young discipline. It's been a little bit tough to pick up on. It's a challenging subject. This is the first year that we've had it in the score sheet, and these folks pulled it off, so congratulations. Okay. Some of the features of that. Started off with innocent point goals, events times, like most of you do. Turned that into very good conceptual level design surfaces, multiple parameters run against each other as potential combinations that are going to yield the results that they're looking for. They did have a fairly limited range of whole car concepts. I would have preferred to see that a little bit more open-ended, but hey, you got to get to competition in June, so I have to stop somewhere. Very good mass model. Okay, for those of you that aren't quite clear what that is, a mass model is, hey, if I put this motor in it and this wing in it, and this is about how much my tub weighs, then all the other pieces are going to have to weigh this much in order to carry them, and you add up every little bit in the car, probably with an allowance for wiring instead of a wire-by-wire mass accounting. And the result is, this is how much that concept is likely to weigh. So mass tends not to be a choosable parameter. Mass seems to be something which follows from, given good mass optimization, the concept, the way that you've equipped the car, the selection for subsystems that goes into it. Mass model is an absolutely vital guide to picking through conceptual design. Okay, middle of the design process. Very good power management survey, very good study of all the power flows used by all the subsystems, all the low voltage systems throughout the competition. These guys, you're not as bad off as your IC cousins, but these machines are very sensitive to all the little parasitic power draws, and that needs to be very carefully optimized. Okay, as far as testing, did a nice job of setting priorities for testing. So they knew what they needed first. They knew what could be given up on if the day was rainy, or y'all have like snow, right? Okay, yeah, serious difficulty. And they also had very clear definitions of when a test could be considered complete and when the car could be considered competition ready as the result of its testing regime. So what I'm trying to say is they really thought their way through what it would take to adequately, logically, and completely test this car. As far as appearance, this is the one that I've actually decided to buy this. You've got the check. Just wait a few weeks before you cash it, if you would. Okay. The car is, look at the shape of the thing. It's not rounded, it's faceted. As long as you're bending in the direction of the flow and being rectilinear across the flow, that's fine. It's a good fabrication section. It doesn't make really any difference to drag and the other bits of aerodynamics, and turns out to be a very handsome shape. We are tapeless. Yeah. The car is clear, the car is clean. As I look at its systems, they're easy to figure out. If I'm trying to repair them at a desperate time in its life, then I'm likely to put my hand in the right place. The motor, suspension, cockpit are all extremely logically laid out, extremely clear. A lot of thought has gone into this and some very careful execution. The aerodynamic attachments, I notice we are also wireless. Okay, all right, you already clapped once. The car is wireless, and look at the attachments of the aerodynamic surfaces to the car. They have satisfied 6 degrees of freedom restraint on each one of those attachments. They have also taken the attachment device out of the flow field as far as structurally speaking, compliance speaking, they could reasonably do so. So what we're seeing is a lot of attention to detail, a lot of thought, a very nice job of building the car, and my best congratulations to all of you.
Well, I think following that, there's nothing else for me to say, really. It is a very nice car. You know, at the beginning I talked about the strength of the monocoque, and how a good illustration of strength is to look at this area here, and that's just what you want. If you want to see a nice monocoque in the right sort of shape for the cockpit rim, that's it, right there. It's almost free, but there are a few wires in the back here still. So, but the difference with these ones is they've been done very well, and the attachment points for them are also done very well. So, full marks to all that. Brackets generally on the car are very nice, but of course I can't leave this without finding something wrong. And to my mind, we shouldn't really be putting pushrod adjusters in the middle of a pushrod, or that should be as far at one end or the other, and generally speaking, they want to be in the inboard end. The farther they are out, the more unsprung mass there is. But so I would like to see any adjusters put as far inboard as possible and right on the end of the push rod next to where it attaches, really. Other than that, well, if I could afford it, I'd buy one myself. Thank you very much. Thank you. Lovely shot. Thank you very much.
Okay, for this car, I would like to talk about the things that the team has done with the dash on the car. And the dashboard on a race car has two jobs. Job number one is make sure the driver, or do everything you can to help the driver not blow the car up. It's job number one. Job number two, you want the dashboard to help the driver drive the car as fast as possible. And those two jobs go somewhat hand in hand with the FSAE competition in EV, because we're back to managing energy during the endurance events. So they have on their dashboard something that all of you can do. They have the state of charge, counting down from 100%, and then they have the distance started at the beginning of endurance, counting down from 100%, so that the driver can see right on the dash, is the energy bigger than the distance remaining? You can go a little bit faster. Is the energy smaller than the distance remaining? Then you should maybe slow down a little bit, save a little bit of energy as you are driving the car. And what I really particularly like about this is that they have used the lights across the top of the dash as an indicator for the relationship between those two values. And they've got a really, kind of for their first implementation, a pretty simple ratio in between those two, but the driver's not doing any math. And the driver, out of the side of their eye, can see the amount of lights that are lit. With keeping it right in the middle, you're right on the pace. You're right on, driving the car exactly the way it was designed to be driven, getting that maximum performance, the balance between speed and energy usage during endurance. And if the lights go up, you got more energy. Go a little bit faster. If the lights go down, you're going way too fast. Slow it down and bring it back to the middle. So don't make your drivers do math. Whenever you can save a driver from doing math, the car will probably go faster. And then the other things that they have benefiting from their switchable torque vectoring and their switchable traction control. So whenever the driver throws that switch, it flashes up on the dash really big that you've gone to this number. So the drivers have learned, this setting for, this setting is going to feel about like this, bigger number does this, smaller does this for each of their knobs. And it's really nice for them to see what number they landed on when they're trying to, somewhat blindly make changes on the car during an event that they're driving. And so that's a nice touch. And then also they have a redundancy where if that system where it's trying to make that number that flashes up, if that fails, the driver still has down in the bottom of the corner a readout directly from the ECU telling them which mode they're in. So I really like that they have two systems on the dash, very simple, for both of those very important pieces of information that are going to help the driver get the most out of the car. So that was a particularly nice detail that all of you can be thinking about. That's you can all be taking the steps to that. You can they're coming for you. So you're going to have to keep getting better. So, and congratulations on design.
All right. Common theme for the top two cars was exceptional use of torque vectoring. But first off, this team did the best job when we were interviewing all the teams of understanding of the tire. and the tire data, all the way to regressing the FX of the rear tire, which they needed in order to do a good job of their torque vectoring. Their torque vectoring approach was to use a feed-forward yaw moment model using steer, lat, and velocity as their inputs. They worked really hard to build a predictable, very drivable torque vectoring. One of the things about torque vectoring, I think, for the driver, for the human, is it can be very counterintuitive. If you start to understeer, sometimes the first thing you're going to do if it's a non-torque vectoring car is you come off the throttle. It's actually the opposite with torque vectoring. So these guys worked really hard to work with their drivers, but also, I think, generating the correct filters specifically for the steering input to generate a really smooth, approachable torque vectoring model. So I was very impressed. And then Chris is going to touch on it more, but they also used their simulation for driver training, which is also extremely important. And I used a term before, the DIL or DIM. It's driver in the loop is the term for DIL. Thank you. Great job.
Yes, so great car. As they've said, it's absolutely beautiful, very well put together. And you guys made good engineering trade-offs in many places, and that includes in the way that you use the data. A common theme amongst a handful of us vehicle dynamics and data judges is that the theory was very good, but we wanted to see more validation and comparison with the data. But then at the same time, what you were doing with your driver reports and like the way that you were using the data to inform your drivers of how they could do better, how you could compare between the different drivers so that they could learn from each other was absolutely incredible. And you're aware that you're maybe not doing as much of the validation, but you're spending the time on the drivers because it makes the car faster. It's going to score you more points. And us design judges, we will grumble at you, but it's probably the right choice. So yeah, I definitely like that. Again, hitting on the accessibility of data, they have a automated process. So when they go out and they run the car, they can very quickly pull the data off and create summaries for their drivers from Python scripts. So it's they're doing well with that trade-off of like how difficult is it to get the data, but they've got established processes for getting the data to the drivers quickly so that they can make changes, learn, and improve. So very well done.
All right, Aero. So anybody who's had a chance to come up and have a look at the car can see the level of fit and finish. As mentioned earlier, there is a little bit of tape, but very little, and it was kind of well thought through in all the elements. That wasn't something that they put together here at the track the day to get through in order to get through tech. So from an aerodynamics perspective, super impressed with the car. This team was able to speak to front wheel wake management better than any other team that I spoke to at competition, and most of the other aero judges had similar things to say. If you look at the way the front wing flaps are, there's basically no inboard end plate and an open slot between the monocoque and where the flaps on the front wing are in order to allow air to come in and get to the floor. So they're actually sacrificing some front wing performance in order to feed air to the floor. They don't have an inboard end fence on those elements, which again is about tripping vortexes and managing front tire wake and the way that it gets entrained into the diffuser and out the back, and their ability to speak to it. I had a really good conversation with the team. In fact, very deep bench of aero team. I mean, there's a lot of people in that conversation having very intelligent things to say. So it's no wonder that they won and that the car is as sophisticated as it is. And I think, as well as, composite shop owner and the fit and finish, it's not something we score directly, but it communicates a level of professionalism, just like all the teams in matching shirts, just like when Peter comes up, the kid takes the little cover over the Multimatic dampers to show them off so Peter can point them out. It's all those little details that kind of set this team apart and made them that like a clear winner and deserving of the design championship.
Before I talk about Wisconsin's car, I just want to talk a little bit about propulsion engineering. 30 or 40 years ago, it wasn't that glamorous. I used to work with an automatic transmission engineer that said, my goal at work is anonymity. Once someone knows the automatic transmission's there, I haven't done my job. But if you look at today, with the advent of EVs and everyone shifting from ICE to EV, battery technology, motor technology, all the kinds of propulsion engineering things, they're the front page headlines in the Wall Street Journal. So it's a really, really big thing, and Wisconsin's embraced that spirit of innovation by designing and manufacturing their own motors. Very few teams here at the competition are doing that. We love to see it. It is super cool. I know that there have been a lot of struggles in getting lots of motors manufactured, carrying out technology transfer one year to another, but it's something that really, really deserves accolade, and I encourage everyone to think about doing it. Again, those make-buy trade-offs are something that you should go in and at least understand how every single component works from the inside out, even if you decide to buy it. So Wisconsin does have hub motors. They've decided only to put 2 on the car due to some part limitations, although they're capable of going in every wheel. As a result, the acceleration time, 4.18, is above the 4-second time, so we'd love to see motors put in every wheel next year, and I know they have plans to do that. The car's super light. I think it was somewhere around 370 pounds. 5 kilowatt-hour battery helps doing that. So again, another team that's really, really critical about battery sizing. The smaller the battery, the better, and you want to make sure that you're using every kilowatt-hour. Even in production cars, batteries are super expensive. I spend 90% of my time on batteries, even though I work on engines, transmissions, motors, all of it. It's where the industry's headed. Try to be frugal with the amount of energy. They have a stressed accumulator. Thank you so much for putting load through the battery pack. I think it's outstanding. It also acts as part of the floor. I don't know, Bill, if you can get your camera slid under the car, but if the battery is the floor, it's like the stressed skin on the bottom of the car and really contributes to the torsional rigidity and lots of other things for aero. So that's super cool. They're also big proponents of regen, which we like. Haven't really talked about it yet, but we encourage every team, to deploy regen. They have calculations of how much it's worth. It can be worth from half to 1 kilowatt hour of battery sizing. So back full circle to how do I get a small battery? Regen's the answer for mass reduction, and the battery mass begets mass in other parts of the car. It affects tire sizing. So regen is a really, really big deal, and it's up integrated in their control system with lifting the pedal, which is outstanding. They also made their inverters, which is great. So again, this spirit of propulsion engineering alacrity and excitement around it was just a lot of fun to talk to the team about. And they also have active cooling inside of their battery pack, fans on the tabs. Again, they've selected pouch cells with a really high discharge rate, so they're good race car cells. And they put the fans in the right spot, cooling the tabs. The tabs, again, usually the hottest spot. They've also integrated the foam springs into the battery accumulator. And I can't stress enough, the accumulator was stressed. So outstanding job. It was awesome talking to you.
All right, thank you so much to our 3 design finalists. If you want to roll out, that's fine. I want to say thank you to all of you for coming to do design judging with us. It's a real privilege and honor to talk to you every year, something we all look forward to. Thank you to the design judges for all the time you gave this week. And I'm excited. We're going to have one more announcement before you leave. You'll want to hear this because we're going to bookend design feedback this year with, we had the panel discussion about autonomous, and here's an announcement about autonomous.
Hi, everybody. I know you want me to do Lost and Found, but I want you to be just a little more patient with us. We have successfully gotten the University of Toronto through autonomous tech, so we are going to give an autonomous demo in the area where the practice track was. So the autonomy demo will be happening immediately after I finish this announcement. We're going to walk out there, if you want to go see it, out to practice. And once that demo is completed, we'll let you know about coming back for awards. Sound good? One more thing from Bill Riley.
All right, in the interest of feedback and continuous improvement, please raise your hand if you like this better than the PowerPoint last year. And please raise your hand if you liked the PowerPoint better. All right, thanks so much for giving us the feedback. Have a great day, and stay tuned for the award ceremony soon.